Hello, dear students. Today we have proposition 15 of book 4, the penultimate of book 4. In a given circle, to inscribe an equilateral and equiangular hexagon, six-sided figure hex. Hexagon, I guess. Okay, let this be your given circle. Thus, it is required to inscribe in this circle equilateral and equiangular hexagon. Once we do that, then the intellect is going to look at the vis cogitativa, that this phantasm in the vis cogitativa, and he's going to say, hey, that's true in every case, and then we can restate the universal. Okay? So universal, particular, intellect using the imagination, seeing the conclusion in that particular, the active intellect hits the vis cogitativa, and they sees the universal. Okay? And the universal is, it is possible in any circle to inscribe an equilateral and equiangular hexagon. Let's start off by finding the center of our circle. Let's do this. There's the center. And let's draw another circle. Let's make that one blue. Okay, another circle. No, let's make it red. Okay, we're going to connect from the center. We're going to connect a line here and make our circle a red circle. Holding this fixed, making a circle. Not very good circle, but that's okay. We're going to have BD. Good enough. And then at these points, we're going to make some connection points here, okay? Do that in blue. Connect these points, these 2 points, and these 2 points, and then connect these points. Man, that's not going to work out very well because the circle's so big. Okay, well, let's have it be. That's life. Okay? Sorry for the ugly drawing. Now, we know that in this circle, these 2 lines are equal because they are radii of the same circle. And we know in this circle, these 2 lines are equal because they're radii of the same circle. 2 things equal to the same, these 2 are equal, and these 2 are equal. Okay, 2 things equal the same thing or equal to each other, so these 2 are equal. Likewise, this would be the same. These are all equal. So this is equiangular triangle. And therefore, being an isosceles triangle, 2 sides being equal, in a 3-sided equiangular figure, if 3 sides are equal, 2 sides are equal. So we have an isosceles triangle, and as much as isosceles also, and therefore the angles at the base are equal. Likewise here, isosceles triangle, therefore the angles at the base are equal. Therefore these 3 angles are all equal to each other. But we know the interior angles of a triangle are equal to 2 right angles. We proved that, remember? That these 3 are equal to 2 right angles because they're equal to these 2. Straight line falling upon a straight line makes adjacent angles equal to 2 right angles. Those 3 are equal to those 2. Therefore, those 3 are equal to 2 right angles. Therefore, in any triangle, the 3 are equal to 2 right angles, and they're all equal to each other. So each one is 1/3 of 2 right angles. Great. Let's continue our lines here. Extend this line. I might as well make it red since the other one's red. And make this one blue. Yes. So all of these now are, okay, let's join these lines up. Boom, 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 boom. Okay, now these are vertical angles. Vertical angles. It's not very pretty, but each of these are then, I got to show that this one here, again, ugly drawing. So this is 1/3 of a right angle. This is 1/3 of a right angle, but here you have a straight line falling upon a straight line, making adjacent angles equal to right angles. We proved that. Therefore, this plus this plus this are equal to 2 right angles. But this is 1/3 of 2 right angles. I'm sorry, I think I said earlier 1/3 of a right angle. 1/3 of 2 right angles, 1/3 of 2 right angles, and then the rest must be 1/3 because it's 1, 2, 3 parts. 1/3 of 2 right angles, 2/3 of 3 right angles, 3/3. So this also is 1/3 of 2 right angles, and they're vertical angles. Vertical angles are equal to each other. We proved that. 1/3 of a right angle, therefore 1/3 of a right angle, 1/3 of a right angle. All these are, 1/3 of 2 right angles. Therefore, all of these are equal. And we know in equal circles, the same circle, in equal circles, equal angles at the center stand on equal circumferences. All these are equal, therefore they're all standing on equal circumferences. Great. And then we know that chords of equal circumferences are equal. chords which cut off equal circumference are equal. Therefore, this are all equal. Therefore, this six-sided figure, this hexagon, even though it doesn't look that way because it's my fault, bad artist, is, we know it intellectually, even though it's interesting, huh? The image is weak, but the intellect says good enough. Thanks, weak artist. It's good enough for me. I still see it. I see it to be so. So our intellect is grasping that this is equiangular. Now let's prove that it's equilateral. Okay, sorry, we proved that it's equilateral. Now let's prove that it's equiangular. Okay, now look. This, where are we? This is equal to this because each circumference is equal. Let's add this circumference to both sides. Okay, let's add this circumference to both sides. Therefore, this is going to be equal to this. Okay, but this angle here is standing on this circumference, and this angle here is standing on this circumference, and this circumference was proven equal to this circumferences. And we know in equal circles, equal angles at the circumferences which stand on equal circumferences are equal to each other. Therefore, this angle, this angle here is equal to, let's say, let me see here, this angle here. We have this angle being equal to this angle. It's a terrible drawing. And therefore, this circumference, which this angle stands on, is equal to this circumference, which this angle stands on. Something like that. This angle stands on. Something like that. Okay? So here we have it over here. I very much apologize for my bad drawing. This circumference here would have this angle standing on it, is equal to this circumference here, right here, which would have this angle standing on it. Okay, so those angles are equal. So this is equal to this, is equal to this, equal to this, equal to this, equal to this. Very much apologize for my horrible drawing. It made it difficult to see at the end there, but that's the case. The circumferences are equal, therefore the angles standing on them are equal. And so we show that the angles are equal, and therefore we can do it for any other angle in that hexagon. Therefore the hexagon is equiangular. Therefore we have inscribed in this not so pretty circle and this very ugly hexagon, we see that it's equiangular and equilateral. Quod erat demonstrandum. Thank you. Faciendo. Thank you. Bye.